Well, we're not done with current measuring yet. I just purchased this Adafruit, the IN219. Well, they call it, it's the 904, the 904 high side DC breakout. But the chip is the 219. Oh dear, I forgot what the chip name was. Anyway, I'll get that. I've closed my computer because I have to solder. But I'll get the chip. I'll get the chip number and the details for it. We'll look at the data sheet. But it's 12 bits. It basically converts from a 0.1 ohm, 1% shunt resistor, which you can actually see here, right here. Let's see if I can get it a little closer on that without fuzzing it up. Nope, sorry. I've got to fix that with the camera or get a new camera. That right there is the shunt resistor. This is your voltage going to come in and out, or current rather, in and out. It's going to go across that shunt resistor. It's going to create a voltage of 0 to 320 millivolts, and that's going to be converted into a digital, with an analog to digital 12-bit analog to digital converter, into I2C, which is going to be read by our Arduino. And they produce a library for it. Adafruit always is very good about completely supporting their products, and they have a library that I've downloaded, so we'll use that. But I wanted to show you how I put this together. I mean, maybe this is just real simple for everybody, but they'll supply you with this little header pin, and of course you get the board, and I've grounded myself, so ESD, and then you just fit the board over where you're going to solder. Fit the board over the headers, the holes over the headers where you're going to solder on here. And I usually put a little support on the other side just so you don't have that lean. You know, there's not much lean there. Let's see if we can see that. There's not much lean there, but it's not perfectly straight. I guess I like it to be really straight. So I put a little support over there, and in this case, I'm just using their, this is where the voltage, the screw terminals are going to come in handy for bringing in the current lines that we're going to measure. But this is exciting because they use a different chip that has all of this built into it, the digital to analog converter, 12-bit. It's going to be, I believe, 0.8 milliamperes down to 0.8 milliamperes and accurate. It goes from 0 to 3.2 milliamperes, or I'm sorry, 0 to 3.2 amps down to 0.8 milliamperes accuracy. It's very exciting to see that. That somebody has put that chip into a breakout board. I hadn't seen that chip before. I look for current measuring chips. We've done the three. You know, so far we've done three different videos with three different types of measuring current. So it's something of interest to me, as you know. And I haven't seen this particular chip, so it's exciting to see this one that really does it all for you. In a sense, because it does the conversion, converts it into a digital format, and then converts that into an I2C, which can be easily read by a microcomputer. In this case, we'll use an Arduino. And then they went to the trouble to write a library for us so that we can easily read it and incorporate it into our own programs. So let's take a look at it. I wanted to show you how I built these. I don't know, maybe you do the same. Maybe this is how you do it, but this is the simplest way to do it. And then just bring over the soldering iron, of course, and touch on each one. And you've got a nice even build, and it's easy to do that way. And it's you don't end up with a crooked header pin across there, a set of header pins across your board. So let me do that, and I'll be right back with you. I just want to let you see what I'm looking at. I inspect my solder joints. So anytime I solder, I always inspect them underneath the microscope to make sure I've done it properly. And I know that's pretty hard to see. I'm looking through just one eyepiece of the microscope, just to give you an idea of what you're looking at here. This is a really nice microscope. I bought it off of eBay. They're about $300, but I'll tell you what, if you can afford it, if you can get it, it's really nice, because there's no substitute for a dual eyepiece microscope when you're now I didn't use this to do this soldering, but when I do SMD soldering, there is no substitute for what you can do with two eyes looking. You get the parallax view going on, but I can see I've done an okay job of this. I know it's hard to see through this camera, but I've done an okay job of doing that, of soldering. And but I just want to let you know what my process was. And there's the board. And I wonder how close I can get, if you don't mind, without, I'm not using the, see, that's pretty good. I'm not using the zoom at all. I'm just bringing it up. And it's got a good macro lens. That tells me that this is actually, as long as you don't zoom, the camera's got a good macro capabilities on it. But there's the soldering, at least of the header board. I still have the current to put on. Here's the resistor. You see the R100 there? That's going to be the 0.1 or the 1 ohm 1% resistor. They might have said 0.1%. I'll have to look. But it's the INA219. Now, what does that INA tell us? That INA tells us this instrumentation amplifier is in there somewhere, is what I think. That would be my guess, is that there's an instrumentation amplifier inside that chip. And that's where the INA is coming from, unless that just means something else. But INA typically means that, is what I found, is that somewhere in the part is a... just make sure I got enough light here. Somewhere in the part is an instrumentation amplifier if I see an INA, but it could be that that's just the way they chose the part number for this. They do have to have some amplification in there. I think they go, it's programmable, we'll look at this, but it's programmable 1, 2, 4, or 8, I believe, for amplification. And now whether you can choose that in the library, I don't know. We'll find that out. But I just kind of wanted to see if this is the way you solder these in, and if that's how you do it, and if that was of any interest to you. And now I've got to put this on, and this one will just go on the other side, and then we'll be able to wire in our current. Okay, we'll see you there. Now, people do ask me, what do you do to clean your circuits after you solder? And what I use is some flux cleaner and a little brush. Now, the one that I happened to pick up, let me back up here. The one I happened to pick up was Flux Wash. And I don't have a particular brand that I go after every time. I'm usually in a place where I have to get what's available, but I found pretty much you get something that's at least it's specific to flux. Keg, I've heard of Keg. Keg's a good product. And Flux Wash, it's a good one. It washes away the flux, what it ought to do. It doesn't hurt the board. It's non-acidic. And but the little brush is important. The little brush that we clean these with is important. It needs to be conductive, because you don't want a brush that can build up static charges as you brush across through through an action of exchanging electrons between the material of the brush, like a toothbrush. I'm no scientist on this. I'm not a physicist or a scientist on this. But if you use a brush that can that's built of a material that can just like when you're brushing your hair, that can exchange electrons with what you're brushing. It seems to me that you can build up static. So a conductive brush, I use these little tiny ones here that I bought at Micro Center. Actually, a Micro Center is a store available in some cities, probably not all cities, but any electronic store that sells Flux Wash or Flux Remover will have some sort of brush like that, and it's meant for electronics. And I just wash it off, and then brush it. I spritz a little on there. Spritz a lot on there, I guess, and just to neaten it up, get that flux off of there, because I do use the flux I use. The reason why there's flux on there, well, it's in the solder, but I use this flux pen, flux pen, and this is the 2331-ZX, and it's like a magic marker, and you wipe across what you're going to solder, and they last forever, and they're really good for laying down just enough flux so that you can put a bead of solder on there really easy. And I'm probably going over this way too much, but I have been asked about it, and I thought I'd go over it, and I'm happy to. I hope it helps somebody. Okay, I'm not going to look at that under the microscope. I'll do that later. I'm too excited about this. Too excited about having this and want to get it up and running. So let's do that. Well, I'm not going to try to duplicate what Adafruit does on their website. They do such a good job. But I did want to look at the data sheet for the INA219 current power monitor. So it actually is a power monitor too, because it's got the internal, as we see here, under description, is a high side current shunt and power monitor with an I2C interface. The INA219 monitors both shunt drop and supply voltage with programmable conversion times and filtering. A programmable calibration value combined with an internal multiplier enables direct readouts in amperes. Okay, so there's where we get our amps reading. An additional multiplying register calculates power in watts. So it multiplies the the voltage times the amps, and it gets power in watts. So that's pretty cool. So we can have a direct readout of watts. Now, I'm not sure if I haven't looked at their library. I don't know if their library takes advantage of that. Probably does, but we'll see when we run the code. And let's see, it comes in 2 grades. Blah blah blah, and it goes down to 0.8 milliamperes. So 3.2 amps, 0 to 3.2 amps in 0.8 milliampere increments with a 12-bit. And there's kind of a block diagram of it, I guess. Let's see. There's your current over here. Programmable gain amplifier, your ADC, power register, current register, voltage register. So there's all your your multipliers and summers, adders, that kind of stuff. And INA, which we knew to be a Texas Instruments designator for differential. See, there it is. There it is. This is a differential. They do use an instrumentation amplifier in there, I bet you. The analog inputs, differential VN plus, VN minus. This is where they initially pick it up. Minus 26 to plus 26 volts. Let's see. I was going to look for the, if there's anything, full scale current sense voltage range. Is okay. Here's our programmable gain amplifier, and I believe ours is set for 8. I think they said it was going to be set for 8 on the Adafruit site. which gives us 320 millivolts output that it will be reading and then you know, doing its conversion with. Let's see, current gain sense error. Okay, it is a 0.1 ohm resistor, which is pretty darn good. So 0.1 ohm resistor is not going to mess with your circuit much. At 1%, high quality resistor. I wouldn't be surprised if the resistor cost as much as the rest of the board put together. I mean, a 0.1 ohm, 1% is pretty good. Let's see. Passages, logic levels. I think that's it for the data sheet. That's just a pinout of, we're not using this pinout, of course, because we're using their board. And, but I think that's it for this data sheet in terms of what we're interested in. Well, I've got it hooked up. I've got power running through it. I didn't show you the circuit. Let me show you the circuit. It's really over a couple of boards here. This is the resistor. This is the external resistor that I just used just to run through so that there's no chance of shorting out my power supply. It's a 1 ohm, 1%, but that doesn't really matter. It's just there to help protect things, help protect the circuit. And we have this external power supply going through the, where's my pointer at? Running it through this resistor into the Adafruit board, in through their 0.1 ohm resistor at 1%, and then back out. That's all it does. So it's just a simple loop through their resistor and out, and just running some current through there. And currently what I'm showing in terms of the current on my power supply, what it's telling me is, as you can see, it's about 1 volt at 0.559, 0.557, 0.56 amperes is what's running through there. And like I say, it's not really important what's running through there. There's just a protection resistor, just to keep things honest. And then there's the board, the Adafruit board. And then we've got the Arduino, of course, excuse me, which is reading the data and then feeding it back to our serial monitor. So let's go back to our serial monitor. As you can see, I'll read up exactly on what these mean. I'll look at this before the end of the video here. But bus voltage, they're showing 1.25 volts. I guess that would be, because I should have 1 volt there minus the drop across the 1 ohm resistor. So it would be only the drop across the 0.1 ohm resistor would be the only thing there. But anyway, bus voltage, and that kind of comes in and out probably with the readings, the registers, however they're read. Shunt voltage is, and that would be the reading directly across the 0.1 ohm 1% resistor that's on their board. So that's 58.27 millivolts. That's pretty stable. That stays there. And then the load voltage, I'll read what that is, what the significance of that is, the load voltage. And then we have the current as would be calculated by all that is 582 milliamperes. Now, is that more accurate than my power supply? It could be. It could be that it's my power supply is saying it's 560 milliamperes, and this is saying it's 582. It could be that it's more accurate, and I don't know. I've actually never calibrated the power supply's amp meter, so I can't tell for sure. What would be interesting is to put something in between there now. Let me do that. Let me set that up, and let's see what a multimeter tells us. Well, guess what? I'm supposed to charge my battery pack. So we'll shut down, and I'll give you the conclusion when we get back. Well, I got the battery charged. I need to get 2 packs, 2 battery packs. Battery charged on the camera, and I did change one thing. I set a parameter in the code so that it would read a little more accurately on the amps, and I'll show you that parameter in a second. But we show for the current, as you can see, 297 milliamperes, 304 milliamperes, and if we look and see what our multimeter is telling us and what our power supply is telling us. Kind of an odd angle there, but that's 301, so we're basically in agreement. We can see that the 300 milliamperes is telling us that the chip is telling us is in agreement, and there is the power supply, and he's telling us at 300 milliamperes is what he's set for. That's actually, he's in current limit mode with a maximum of 300 mils, and so that I went ahead and just left it that way. But 300 mils, and as we can see with the swing it around, as we can see with what the chip's telling us. Where's that blue coming from? There we go. 300 mils there. And so it looks like it's the most accurate sensing that we've seen so far. We've seen this would be the 4th current measuring system that we've seen, and I believe this is the most sensitive that we've seen, and possibly the most accurate that we've seen. And I wanted to show you this INA. This was called INA, and I was figuring that's an instrumentation amplifier. And if that looks familiar to you, we have the current shunt resistor, and now what they've got here, this is for a different purpose. But basically, then they've got these 2 resistors here, and it comes down and goes into this programmable gain amplifier, this PGA. Well, this basically is our instrumentation amplifier. And where do we remember that from? That was from our first video. Let me just plop this down. Our first video on measuring current. And if you remember our instrumentation amplifier here, just in a block, it's just a big block, but inside there's an op amp. It would be a triangle in here. And there's our current going through our shunt resistor. And then we had a gain resistor on it, which most likely internally they have gain resistors internally on the one that we're looking at, the current one that we're looking at. But we have the instrumentation amplifier, so we've actually done this before. So these would be very similar in that both of them use instrumentation amplifiers. They're difference amplifiers. It's multiplying the difference between the voltage on either side of the shunt resistor, and then from that getting the current, either applying the current from the voltage, because you know what the resistor is. so your value is. So if you take the voltage, you're going to know what the current is, which is what the current one does also. This one, he's just taking the known resistor value, and from that can determine what the current is going through it based upon the voltage across the resistor. In this case, this one has a lot more. He's got the digital analog converter, or I'm sorry, the analog to digital converter. He's got where he reports current. I think those lines are showing up. He can report current, voltage, and power. Although we haven't seen power, I don't see in the set of commands that Adafruit put out in their library. I don't see where they're offering the power, but power can be derived from the current and the voltage. So you can kind of do that yourself if you want to, just by deriving that. But the parameter that I set here, and I'm just going to move this over. Get that in where we can see it. The parameter I set that they create is this one here. Let me get that to where you can see it. This one here, where it's that you can calibrate it for a maximum of 400 milliamperes, 16 volts, and it will create a higher precision on volts and amps. So I just wanted to try it and see what it would do, and it definitely is very precise, and looks like if you're not going to go over 400 milliamperes, that would be you'd want to set that value, and you just comment that out if you want to go with the standard one, which is the 32 volts, 2 amps. And they've also got one where you can get a higher precision than the amps by itself, and that's this one here, set calibration for 32 volts, 1 amp, so you can have a maximum of 1 amp, and a higher. That way you can get a higher precision, because your 12-bit analog digital converter then is then divided into just the 400 milliamperes or the 1 amp, so you have a more precise steps, a higher precision of steps between one or the other. Instead of 0.8 amps, it would be 0.25 amps or something like that, or 0.25 milliamperes instead of 0.8 milliamperes would be the precision step. I don't know if it's 0.25, but that's just an example. I haven't calculated it. It would be 2 to the 12. It would be 400 milliamperes divided by 2 to the 12, whatever that is. 2 to the 12th power, and then that would be your step in amperage. Or you can have 1 amp divided by or 2 to the 12 divided by 2 to the 12 power, and that would be your step for your middle. I guess you'd call that your middle range. But anyway, this was our 4th look at measuring current, and I think we've covered the gamut on this one. I think we've gotten I think what I might do now is just simply maybe show it in action. Show it actually measuring something instead of just a test signal, actually showing something useful, and showing it measuring. That would be the only other thing I could think of that we could do that would bring out the usefulness of a current meter like this. And thank you, and thanks for watching. Well, I couldn't resist. I had to measure something. So what we're measuring is the current in this that goes into this Mega, this Arduino Mega 2560. And this is the setup we saw before. This is the INA219 or something. I've forgotten now, but this is our INA current measuring, current sensing device. This is our Arduino that's sending back the information back to running the program, sending the information back to the computer. And this is just the mess of wires that sends the voltage. The voltage first comes out of the power supply, goes into the Arduino, goes to the current sense, and then back to the power supply. So very simple. Even though it's got a lot of wires there, it's very simple. And what are we seeing on our current? I'm just going to swing that around instead of stopping it. What we're seeing is 33 milliamperes. And we know we're pretty accurate with this now. We've seen the accuracy of this. So that Arduino Mega takes 33.4 milliamperes. We can just say 33 milliamperes. That's what it takes. Is on just not running, just sitting there idle, nothing hooked up to it. We know that that's what the Mega takes. So I thought it would be interesting to measure something that was real. Instead of just a dummy load. And that's kind of curious. Now, how does that compare with a Arduino that's got some, oops, yeah, there we go. Off camera here, I'm going to unplug the Mega. There it is, unplugged. Went to 0. I'm going to plug in an Arduino, a regular Arduino Uno, that's hooked up to the color sensor, the tiles color sensor. And look at there, 36 milliamperes. So the Mega takes a pretty good chunk, because I've got the Arduino with 4 LEDs hooked up to it, with the tiles color sensor hooked up to it, and a program running, and that's 36 milliamperes, where the Mega just on its own doing nothing was 33 milliamperes. So that's a pretty interesting contrast between the two. I actually thought it would have been taking a lot more with the 4 LEDs. Interesting. Okay, well, there we go. I think that completes it. I appreciate your patience, and I hope you found that as fascinating as I did. All right, bye-bye.